Matrix. H.G.TIWARY, Supervisor at DFCCL, Girirdi. I am going to start matrix in this connection. First of all, I taught what is matrix, kinds of matrix, operation on matrices. Now today, integral power of matrices. Suppose A is a matrix. Then positive integral power of matrices, that is a square a into a cube a square into a4 a cube into so on. In this way we can find integral power of matrices, so on. Now we have to study matrix polynomial. Matrix polynomial, as you know, fx a0 a1x a2x square, in this way an xn is a polynomial of degree and if A is a matrix of order is a square matrix, a square matrix of order n, then if A is a matrix polynomial or matrix A is equal to A0 in an a1 a2 a square an a to the power n. It is a matrix polynomial on matrix A square matrix A having order n, where in is the identity matrix of order n. Fx is a polynomial x squared 2x plus 5, and A is a square matrix of order 3, then Fa matrix polynomial on square matrix A square 2a plus I5 I3. This constant will multiplied by corresponding identity matrix. If A is a square matrix order 3, then it is 5 will be multiplied by identity matrix order 3. If it will order 4, then this will multiplied by I4 accordingly. So in this way we can find matrix polynomial. So this is the regarding matrix polynomial. Now we come to the point transpose of a matrix. Transpose of a matrix. If A is a matrix of 3:3, it is a square matrix A, then transpose matrix is denoted by A transpose, and it will be obtained by changing rows, corresponding rows into column. First row converted into first column, second row converted into second column, and third row converted into third column. So this is the transpose of a matrix A. So if you take another example, if B is a matrix A, B, C, D, E, F, order is 2 row, 3 column, then transpose of B, transpose of matrix B is equal to B transpose, and first row converted into first column, second row converted into second column. So order will be 3 rows, 2 column. There is a 2 rows, 3 column, it will be 3 rows, 2 column. This is the transpose of B matrix. So rows will be converted into corresponding column and order will be interchanged. It is 2 by 3, now it is 3 by 2. It is transpose of a matrix. In this way you can write transpose of a matrix. Now in this transpose there is certain laws of transpose of matrices. First, A transpose to transpose A. It is first law. Second, A plus B transpose is equal to A transpose plus B transpose. Now, third, K into A transpose is equal to Ka transpose. Fourth, reversal law of transpose of matrices A into B transpose is equal to B transpose into A transpose. So these are the laws of transpose matrix. Now we will study symmetric matrix and skew symmetric matrix. Symmetric matrix and skew symmetric matrix. So first of all we see symmetric matrix. You should know symmetric and skew symmetric, they are also a square matrix. Only a square matrix will be symmetric and skew symmetric. So symmetric matrix A square matrix A is said to be symmetric matrix if A transpose is equal to A. If A transpose is equal to A, then it will be said to be symmetric matrix. A square matrix A is said to be symmetric if A transpose is equal to A. As for example, if A is a matrix A, C, it is a square matrix of order 3. If we find transpose of A, first row into first column, second row into second column, third row into third column, so again it is equal to A. Here we have seen that A transpose is equal to A, therefore this is a symmetric matrix. So this is a symmetric matrix. So any square matrix satisfy this condition is called symmetric matrix. This is called symmetric matrix. Now we come to the skew symmetric matrix. Skew symmetric. A square matrix A is said to be a skew symmetric matrix if A transpose is equal to minus A. Any square matrix A satisfying this property is called skew symmetric matrix. A transpose is equal to minus A. This is the definition of skew symmetric matrix. Example of skew symmetric matrix. We can take example of skew symmetric matrix minus 5 0 is a square matrix order 2. Then A transpose first row, first column, second column. So we see that if we multiply each element by minus 0 0 minus 5, that is 5 0, this is equal to minus A. Therefore this is a skew symmetric matrix. A skew symmetric matrix. One property of skew symmetric matrix that diagonal elements are always 0. Diagonal elements of skew symmetric matrix are always 0. Diagonal elements of skew symmetric matrix are equal to 0. Now, A transpose is equal to minus A if A is Aij and A transpose Aj. So for skew symmetric A transpose is equal to minus A. So AJI is equal to minus AIJ. So if I is equal to J, so AII is equal to minus AII. So AII plus is equal to 0. So 2AII 0. So AII 0 by 2 0. Therefore I is equal to 1, A1 1 0. I is equal to 2, A2 2 0, so on. So diagonal elements of skew symmetric matrix are always equal to 0. Now there is a theorem where matrix every square matrix can be expressed as sum of symmetric matrix and skew symmetric matrix. Proof: if A is a matrix, A can be written 1 by 2, A plus A transpose plus 1 by 2, A minus A transpose. We can write in this way. Let consider this is P, this is Q. So we see that P is equal to 1 by 2, A plus A transpose. Now P transpose is equal to 1 by 2, A plus A transpose का whole transpose. So transpose, it will as per the property of A transpose. A transpose A transpose plus A. This is again equal to P. Therefore, P 1 by 2 A plus A transpose is a symmetric matrix. Right. Further, Q A minus A transpose. This is Q. Take Q transpose 1 by 2 A minus transpose, then 1 by 2 A minus A transpose this is A minus A transpose A transpose minus A transpose A. So minus common, A minus 1 by 2. So minus 1 by 2 A minus A transpose. So we see that equal to minus Q. So Q is a skew symmetric matrix and therefore A 1 by 2 A plus A transpose 1 by 2 A minus A transpose, that is P plus Q, that is symmetric matrix plus skew symmetric matrix. In this way, any square matrix can be expressed as sum of symmetric matrix and skew symmetric matrix. This is regarding symmetric and skew symmetric matrix. Now, problems for homework.